4 बज गया रे। Hello guys, good evening.
Good evening, sir.
Yeah, good evening. Okay. Okay, could you see the screen now?
Yes.
We have discussed yesterday SN1 SN2 reaction, correct? And we have already discussed that what happens if for SN1 reaction, what are the conditions, and the substrate, which is the alkyl halide. If you have 3-degree alkyl halide favors this kind of reaction, 1-degree alkyl halide favors SN2 mechanism. Okay. Yeah, SN2 mechanism. So like we were discussing about what happens if you have 2-degree alkyl halide. So in case of 2-degree alkyl halide, I have told you that the mechanism of the reaction, it depends upon the nature of the nucleophile and the solvent. Okay, so you see here, suppose we have nucleophile, we have solvent, and the product by which mechanism? Okay, product by. So if you have neutral nucleophile, if the nucleophile is neutral, solvent is polar protic. So we know polar protic solvents favors SN1 reaction. So mechanism is SN1. This is, we are talking about secondary. Okay, SN1 mechanism will be there. If the nucleophile is negatively charged, and the solvent is polar aprotic, and we know polar aprotic solvent favors SN2 mechanism. All these we are doing for 2-degree alkyl halide. Okay, so neutral nucleophile is comparatively weak. That also we have discussed. Negatively charged one is comparatively strong. Okay. Now a few examples we see. We have substrate here, SN1 and SN2. If the substrate is CS3Cl, so it is 1-degree alkyl halide, mechanism can not be SN1, but it is SN2, favors SN2. Similarly, if you write down the another one, CS3CH2Cl, SN1 is not possible, SN2 is possible here. If you have CH3F, Okay, so SN1 obviously not possible, 1 degree. SN2 is also not possible into this because of the strong carbon fluorine bond. Okay, if you have tertiary, for example, CS3 whole thrice CBr, so SN1 possible, SN2 not possible. Not possible means what? The major product is according to SN1. Okay, not SN2. That is what it means. If you have secondary halide CS3 CHCl CS3, okay, SN1 favors here, SN2 also favors here, right? But the condition of SN1 is we must have weak nucleophile, okay, and for SN2 we must have strong nucleophile. Okay, like I said, in 2 degree both mechanism possible. If strong nucleophile we have SN2, weak nucleophile we have SN1. What happens in this molecule? Could you tell me? SN1 or SN2? SN1 or SN2? Tell me. Yes, guys, in this one, tell me the first one. SN1 or SN2?
Is it
Am I audible?
SN2, so
See, in this one, phenyl cation is not at all stable. Okay. You see, this phenyl cation is not stable. So SN1 is not possible. SN2 is also not possible because of the partial double bond characteristics we have here. Okay. Carbon chlorine in this aryl halide has partial double bond characteristics because of the plus M effect of chlorine, and hence difficult to break the bond. SN2 is also not possible. In this one, the alkyl halide is 1 degree, so SN2 possible. But when you remove this halogen atom, you'll get positive charge here, which is resonance stabilized, benzyl carbocation. So in this case, SN1 is also possible. SN1 is possible when the nucleophile is weak. Again, the same condition, weak Nu, and this is strong Nu. One degree halide, SN2 possible, and this carbocation is allylic carbocation, so SN1 also possible. Again, the same thing, weak nucleophile and strong nucleophile here. This 1 degree halide, SN2 possible, and carbocation is dancing resonance stabilized, right? So SN1 also possible, weak nucleophile, strong nucleophile. Done, all of you?
so 1 minute.
Copy it down.
Yes, I done.
Just a second. Just a second, guys. Yes. So these are the few things, few example you have that you must keep in mind for SN1 SN2 mechanism. Okay. Now the another type of nucleophilic substitution reaction is SNi reaction. These reactions are not that important. Okay, but we'll see one example of this. What is this reaction and how do we get the product along according to these reactions. Okay, I stands for intramolecular. Okay, so this reaction in which the nucleophile and the leaving group present in the molecule itself. Okay, this reaction is possible in which, write down, molecule in which the nucleophile and leaving group present in the molecule. For example, if you take this example, OH, CH2, 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 okay. Now you see this OH here behaves as a nucleophile and this is the leaving group, okay. So because of this high electronegativity of this thing, chlorine, this carbon becomes delta positive, this becomes delta negative. And this OH behaves as a nucleophile, it will attack onto this carbon atom and this Cl minus goes out, okay. So we'll get a cyclic ring here which has 1, 2, 3, 4, 5 membered cyclic ring we get, in which the oxygen is present in the ring itself. This H will be here, this hydrogen, and O will have the positive charge since it donates its electron to this carbon atom. Now to stabilize this positive charge on oxygen, H plus comes out and we get this, the molecule. This is the product of this compound. Okay, so we can have OH here. Another example you can take for this, like instead of OH, if you have NH2 present, okay. So for example, okay, this lone pair, it attacks onto this carbon atom and this goes out. So again you see we'll get a 5-member ring in which nitrogen is present in the ring itself. The positive charge on it. And the last step, H plus comes out, minus of H plus here and minus of H plus here. The final product is this. Understood? Could you write down the product in this reaction? What is the product in this reaction? Tell me the product.
So a six-member ring will be formed along with O in the ring attached to the benzene one.
Okay, so we have this compound. The benzene ring will be as it is, and we get a six-member ring, and this OH, oxygen, is present into the ring. Okay, so this H plus that we are removing here, this actually takes place in presence of a base. Okay, so everywhere we have a base here, then the removal of H plus will be easier, right? So these reactions, SNi reaction, takes place in presence of a base, which we use in the second step to remove the H plus as proton. Okay.
So in the first step, the condition can be anything.
Sorry?
In the first step of the reaction, the condition can be anything or some specific.
We are just, no, here we do not have any condition. Obviously, we are using some temperature here. Like we'll have the reaction temperature here, but we are not heating it. We are not providing any catalyst or anything else. Just this behaves as a nucleophile because of separation of this charge, and this will attack onto this. To remove this H plus, we are using the basic medium.
Okay.
Okay. Next reaction is SNngp. SNngp. This NGP stands for neighboring group participation. Neighboring group participation. Okay. So this reaction, it goes like this. Suppose we have a compound, and the condition of this reaction, I'll tell you what is the condition. Suppose this is a compound we have, six-member ring, and here we have sulfur phenyl. It is present here. Sulfur has, it is similar to like phenoxide ion, OPH. Instead of O, we have sulfur present here. This is the hydrogen, okay? And here we have one hydrogen and chlorine present. So what happens here? This is a nucleophile. Like in the earlier one, we have OH as the nucleophile. Here we can have SH We can have OPH also here, SPH also here. So this sulfur, the lone pair on this behaves as a nucleophile. And for this SNngp reaction, the leaving group must be present opposite to this nucleophilic group. Okay. This reaction again, it is taking place in presence of a base. Okay. And the product that we get here, when you have OH, it is this SPH, H, here we get OH, and here we get H. This is the product of this reaction. This OH, you can say, it simply replaces the chlorine atom, which is the leaving group here. Okay. Now, the mechanism of this is, what happens, since this is partial positive and partial negative charge, so this behaves as a nucleophile, it attacks on this carbon atom. That's why it must present opposite to this nucleophile, the leaving group, so that backside attack is possible. When this attacks over here, this goes out as a leaving group, and this is nothing but the SN2 attack. Okay, so what we get, you see, SPH, positive charge. This is the this thing, the intermediate we get. Now the base that you have, the base also behaves as a nucleophile and attack here through SN2 mechanism backside. So when this attacks here, this goes up onto the sulfur atom and it gives you this SPH, OH, and H will have this side. This is the product we get. So it is the participation of the neighboring group. SPH is the neighboring group of this. So hence we call it as neighboring group participation. Two properties of these reactions are important. First of all, the configuration does not change into this. Configuration does not change. Means what? If it is R, this also will be R, R and R. Here the backside attack, see, here we have Walden inversion, R becomes S, SN2 Walden inversion, R becomes S, again we have SN2, so this R becomes again S. So net effect is what? There is no change in configuration. So configuration does not change. Another thing, the rate of this kind of reaction is almost 1,000 times of SN1 or SN2. Okay, you don't have to memorize this number, but you should keep this in mind that the rate of reaction of SNngp is far more than the SN1 or SN2. So this one will have the opposite configuration of the initial molecule. This one will have the same configuration. Okay. Now, write down next. The examples of SN reaction, nucleophilic substitution reaction. What are the examples we have? So first example we are going to see on halogen derivative. We have discussed this thing in the chapter alkyl halide and aryl halide. Once more we'll do this. You can understand the mechanism of the reaction here. Okay. And the first reaction we have in this, the reaction with KCN or NaCN. Okay. So if the reaction is this, suppose we have RCl and this is allowed to react with KCN or NaCN, right? What is the product we get here? RCN, right? If you have RCl and this reacts with AgCN, what is the product we get?
RNC.
RNC. What is the reason for this?
So KCN is ionic, AgCN is covalent.
Okay. So this we get cyanide. Since KCN is ionic, and this we get isocyanide since AgCN is covalent. So what happens if it is ionic and AgCN is covalent? And then what difference we have in the two? How does it affect the product of the reaction? Any idea? No?
So the ionic one will have a free end which has like the lone pair which can attack. I think so.
Not, you're not audible.
Sir, I'm not sure any difference.
Just a second. See what happens when you have ionic compound like NaCN or KCN. Then actually this gives Na plus and Cn minus. Cn minus. So Cn minus is what? It is the term, one term we use here. It is ambidentate ligand. Ambidentate ligand. We'll study this in coordination compound. Okay. Ligand is the compound or ion which donates a pair of electron. That is a ligand. Okay. Ambidentate means the ligand which has more than one site of donation of electron. Like you see here, what happens? Carbon can also donate electron to the this thing, alkyl group. Nitrogen also has lone pair, so it can also donate electron to the alkyl group. So when RCl allows to react with NaCN or KCN, this NaCN dissociates as this, and then this behaves as a nucleophile. So here we have both end to attack onto this positive charged carbon. So if carbon attacks here, we'll get RCN. If nitrogen gives this pair of electron to this alkyl group, we'll get RNC, and Cl minus goes out. Okay. Now we cannot eliminate the formation of this isocyanide in this reaction with NaCN and KCN also. But obviously this will be minor. It forms in very less amount because the electron donating tendency of carbon is far more than to that of nitrogen, since carbon is less electronegative. So what we take, that carbon is mostly donating electron to this alkyl group, and hence RCN forms as a compound, right? Unlike what happens in this thing, AgCN is covalent in nature. So this will be like this, AgC triple bond N and lone pair on it. So this side, this carbon is already associated with sulfur. This is not the open end, right? So carbon cannot donate electron to the alkyl group. That is not possible. Hence, nitrogen donates electron to the alkyl group, and we get R and C as the final product into this. So with AgCN, RNC won't form, RCN won't form. This won't form. But here, a small amount of isocyanide along with cyanide also forms. Understood this? Clear?
So the product with AgCN will be less stable compared to the product with NaCN.
What?
So the product with AgCN,
Huh?
RNC, that will be less stable than RCN.
No, in this one you're talking about. In this one, RCN won't form.
Yes, sir, but the compound as such, I'm comparing RNC
This
and
and this we are
RCN.
comparing.
Yes, sir.
This and this we are comparing. What we can say? Yeah, we can say RCN is more stable because we have a better, strong bond we'll have here, stronger bond here. But yes, this compound and this compound comparison, stability comparison is not there. But if you have to compare, we have carbon-carbon overlap here. This compound is slightly more stronger or stable than this one.
Okay.
Okay. Same type of reaction we have with KNO2 and NaNO2 also. You see this reaction? Reaction with the mechanism of the previous one is SN2. Write it down. SN2 mechanism. And KNO2. You see, these are also ionic compounds. So this dissociates as K plus and O minus and double bond O. Like this it forms. So here oxygen is the donor atom, right? Oxygen is the donor atom here. So when it reacts with RCl, with NaNO2 or KNO2, this converts into RO and double bond O. Okay, we get here nitrite. This compound is nitrite. But when the reaction takes place with AgNO2, this leads to the formation of ON double bond O and a lone pair here, right? So here what happens, oxygen is attached with silver, right? It's a basic, covalent compound. It is attached with this. So donor atom is nitrogen here. With the same logic, donor atom is nitrogen. So with RCl, it converts into, with AgNO2, it converts into nitroalkane, RNO2. Right? This is nitroalkane. Understood? Okay. All these reactions are SN2. Okay, so write it down. All these are SN2 and keep this in mind, that no carbocation formation into this, no rearrangement. There are some other examples of SN2 reaction. Write it down. aqueous KOH, CH3ONA with CH3OH. Write down the product in all this reaction. We have RS minus Na plus CH3 minus Li plus. Just you identify nucleophile and that attached with the alkyl group, SH minus. What is the answer in the first one? The answer will be ROH. This alkyl halide is 1 degree, I'm assuming, and hence all the reactions are SN2 reaction here. Okay, nucleophile is what? This K plus takes this Cl minus, and this OH minus behaves as a nucleophile here. Or you can take water molecule also as a nucleophile here. Here the nucleophile is CH3O minus. So the product is ROCH3. Here the nucleophile is RS minus. So RSR the product is. Here the nucleophile is CH3 minus. RCH3 product is. LiALH for the reducing agent, hydride ion is produced, product is RH. H minus will get attached over here. RSH, product is thiol, RSH. SH minus is the nucleophile, product is RSH. All these reactions are SN2. The mechanism is SN2, inversion in configuration takes place.
Sir?
Yeah.
Sir, what is the compound called when there are two alkyl groups attached to sulfur? Like in the third example.
What is this? ROR.
Ether.
Alkoxyalkane.
Yes, ether it is, correct? Alkoxyalkane also correct. Ether, alkoxyalkane. This one is thioether.
Yeah, okay.
This one is thiol. SH is thiol. Okay. Another reaction is the reaction with silver oxide, Ag2O, dry. And the reaction with Ag2O, moist. Dry means there is no water present here, no H2O, and moist means in presence of water, of H2O. So the reaction is, if you have RCl, 2 molecule of alkyl halide we are using, with Ag2O dry, we'll get ether here, that is ROR. The product is this. But if you have 2 RCl, or if you have moist, then we'll take only one molecule with Ag2O moist. The product will be ROH alcohol. Okay, this is the difference we have here. Now, why these two different products we are getting? Yes, if the molecule is chiral, Anirudh, okay. If the given RCl is chiral, then the configuration will get reversed. If it is not chiral, not optically active, then there is no point of talking inversion in configuration. Okay. Okay.
So both of these are SN2.
SN2. All these reactions are SN2. Whatever we are doing, SN2 here.
Okay.
Only SN2 reaction we are considering. Means in halogen derivative, what all reactions are SN2 reactions. So what happens, you see, we have Ag2O, right? So the molecule is this. And this is allowed to react with the alkyl chloride, this is RCl. And the product here we get is this lone pair attacks onto this alkyl group and Cl minus goes out. So you'll get AgOAg plus and Cl minus. Okay. Now from this, Ag plus comes out, okay, leaving this electron pair to this oxygen. It forms then AgOR and Ag plus goes out, which combines with Cl minus forms AgCl. But in the next step, what happens? This AgOR reacts similarly with the another molecule of RCl, since we are using two molecules of this. Okay. And same reaction, this comes over here. This comes over here and this goes out. So it forms AgOR positive charge plus Cl minus. Further from this, Ag plus goes out and it forms ROR and Ag plus, right? Again, these Ag plus and Cl minus combines forms AgCl. So apart from this ether, we'll get two molecules of silver chloride here.
Sir?
Yeah.
Sir, if the alkyl halide is 3 degree, then also SN2 over here.
No, if alkyl is 3 degrees, then it favors SN1 reaction.
Okay, this is only for 1 degree.
Yeah, it's got SN2 only. See, we are talking about SN2 reactions now. Okay. SN2, SN1 both are a comparative reaction. Okay. If you are taking 3 degree alkyl halide, then the reaction has more tendency to go via SN1 mechanism. That is what we can say.
Okay. Yes.
Okay. So all these alkyl halide are 1 degree we are considering. Now in this, what happens? Ag2O, since it is moist, so water also present here, it combines with this and forms two molecules of silver hydroxide, which produces 2 Ag plus and nucleophile is OH minus. This nucleophile attacks onto this and forms RCl plus OH minus. It gives ROH and Cl minus goes out. So this step is SN2. This step is SN2. This is SN2. So alcohol we get when we have moist silver oxide, ether when it is dry.
Sir, this is more than one step. So how is it SN2?
Sorry?
Sir, this is more than one step reaction. How is it
No, it's not
SN2?
more than one step. I have written here to make you understand this. All these, see, this is SN2, this is one step reaction. It ends up here. This won't form, it is an intermediate. This gives you this. And then again SN2, this gives you this.
So, but SN2 doesn't give an intermediate, right?
No, it forms during the, see, what happens, it's not like this, this forms into this and then this converts into this. Means when it has tendency to attack onto this, so we'll have an intermediate step, no, that is trigonal bipyramid. I've discussed yesterday that this bond, O and R bond is about to form, R and Cl bond is about to break. That instant we are talking about is this.
Sir, but you've drawn a carbocation, so that carbocation doesn't form as such. It's just a transition
It won't
state.
form. It won't
There's
form.
no carbocation.
Not
It's
carbocation, sorry, whatever. The positive charge on it.
on oxygen, right?
Yes, sir.
Yeah, this won't form. It is like you can say it is an intermediate. The transition state of this into this. In between, somewhere in between these two, we'll get this, which further converts into this.
So the two steps you have written happen simultaneously, sir.
Yeah, so it is not two-step actually. I have
Okay.
written here to make you understand how the reaction is proceeding. When you do
Okay.
this reaction in the lab, you'll see this plus this gives you this and this AgCl.
Okay. So SN2 happens twice. So again here, if it is chiral, then there won't be any inversion.
Inversion. Always. Whenever SN2 is there, if the compound is chiral, the configuration get reversed.
Yes, so it's happening twice over here. So the ether won't be chiral.
No,
So, I
see,
mean, sorry, the ether won't be involved.
we are talking about configuration of this and product. We are talking about
Yes.
configuration of this and product, right? So this you see, if this is R, correct? So this will be
Yes.
S here,
Yes.
right? So if it is S, this becomes R. So each step you see, this one to this one, right? The configuration get reversed, no?
Okay.
The entire thing, see, why you are getting confused? Because I have written this in two steps, okay? But all these things, this from here to here, this is not happening. This is not happening like in this stepwise manner. I have written here to make you understand this. Okay.
Yes. Yes.
This
Understood.
actually what happens, the overall reaction will write this. This plus this gives you this plus this. अब इन दोनों के बीच में ये सारा कुछ हो रहा है. So I have written
Okay.
here to make you understand. Okay. Right. So this you must keep in mind. Moist gives you alcohol, dry gives you ether. Okay. Another reaction with, write down, with NH3 derivative, ammonia derivative. Again, this reaction is SN2, sorry, with NH3. Could you write down the product in this? Tell me the product here. Tell me the product in the first one.
RNH2.
We'll get RNH2 plus HCl. How this happens, you see. First one I'll explain. RCl plus NH3. NH3 has lone pair. This attacks onto this and this goes out. So you'll get RNH3 positive charge on this Cl minus. To stabilize this positive charge, one hydrogen atom comes out as H plus. So it forms RNH2 plus HCl. This is the product we get. So it is primary amine, the product is. Here we get RNHR plus HCl. Similarly, we get this also. Secondary amine. Here what we get? It is tertiary amine, 3-alkyl group. What is the product here? No reaction. With NR3, it does not react because there is no factor which stabilizes this positive charge on nitrogen atom. If you have at least one hydrogen, this hydrogen can come out to stabilize the positive charge of nitrogen here. But here we do not have any hydrogen atom, and alkyl group cannot come out as R minus, R plus. Okay, it is not possible. Hence, this does not react. Okay. Another reaction is Williamson ether synthesis. This reaction is there in alcohol chapter, alcohol phenol ether. Okay, we are doing this here. The reaction is what? Again, it is SN2 reaction. And it forms RCl with R minus ONA plus alkoxide ion we are using. Oh, I'm sorry. This is RO minus, I should write. Suppose I'm taking this R as R1. R1 O minus Na plus. It forms ROR1 plus NaCl. This is the overall reaction. Now, a few examples of this you see. Suppose I am taking CS3O minus Na plus CS3Cl, 1 degree. It is also 1 degree. This is also 1 degree. So it forms what? Tell me the product here in the first one.
CH3O CH3.
Plus NaCl. Here. Correct?
Yes, sir.
In this one?
Sir, no product.
Why no product?
Because tertiary
3 degree alkyl halide.
It is 3 degree. So the attack of nucleophile is very difficult here. This is not possible because of this 3-methyl group present here. And another thing, it is 3 degree alkyl halide. It has tendency to go under SN1, which is not possible here, right? Because the nucleophile is strong, but alkyl halide does not, allow the nucleophile to attack onto this because of its complex or tertiary structure. That's why this does not give any product in the reaction. So for Williamson ether synthesis, the alkyl halide must be 1 degree or smaller groups, right? So if I have to form this product by Williamson ether synthesis, could you tell me the reaction? I'll write down here. By which we can get this product OCS3 plus NaCl. What are the reactant we should use for this particular product? What is the formula of alkyl halide here? Yes. Alkyl halide should be this, because we prefer to take this as 1 degree. And the nucleophile is this, O minus Na plus. If this is an alkyl halide, so the nucleophile won't attack onto this carbon atom because of the ring structure. Okay, so in Williamson ether synthesis, the mechanism is always SN2, right? And the smaller alkyl group always goes with the alkyl halide. Done? See, I have discussed two reactions in alkyl halide chapter, which is this one. What is this reaction? Have you remember this reaction?
Yes.
Halide exchange, right? So halide exchange, for example, we have RCl with what is the reagent?
NaI and
In
acetone.
presence of acetone.
Na acetone converts RCl into Ri plus we get NaCl,
Here.
precipitate of this. Even this reaction is also true with bromine. Same reagent will get RBr plus NaBr, Ri plus NaBr, I'm sorry. All these NaCl and NaBr forms precipitate because its solubility is very less in acetone, right? So it forms precipitate and we can take this out easily. Okay. But like this carbon fluorine bond is very difficult to break because the size is small, bond strength is very high. So for fluoride, we use here Schwartz reaction, which is this RCl, and we use here some fluorinating agent. AgF we can use, which gives you RF. This fluorinating agent we can have, the other reagents are Hg2F2 we can also use for this purpose. We can also use COF2, etc. Okay, all these reactions follows SN2 mechanism. This is also SN2 mechanism. Okay. Understood? Okay. Now there are a few reactions of alkyl halide which follows SN1 mechanism of halogen derivative. Okay. We know it always takes place in polar protic solvent. So if you have polar protic solvents like this, it follows SN1 mechanism with the substrate must be tertiary, 3 degree, correct? With ROH. What it gives? Tell me the product here. Product is OR. Are you getting it? Tell me fast.
Yes, sir.
See what happens here. This ROH alcohol behaves as a nucleophile. This Cl minus first of all goes out and forms the carbocation. SN1, so we'll get a carbocation first and Cl minus goes out. Now on this carbocation, this ROH behaves as a nucleophile, attacks onto this, and then finally H plus goes out to stabilize oxygen, you'll get this. Clear? Understood? PHCH2Br with H2O. Tell me the product.
First reaction will be PHCH2OH.
Where? Yes. First of all, Br go, and why this is SN1, that also you try to understand. This one is tertiary SN1. This carbocation is benzyl carbocation, is stable. That's why this follows SN1 mechanism. It forms carbocation first and then nucleophile attacks. Nucleophile is H2O, product is PHCH2OH. This one, tell me. What is the product? Is this right? First, it forms carbocation. This positive charge here is resonance stabilized. You see this carbocation in this, the third reaction. The carbocation, we get this, which is resonance stabilized with the lone pair of this. Okay, that's why the carbocation forms. And then water as a nucleophile attacks onto this, forms OH. Clear? Understood?
Yes.
Now, the another reaction is, write down nucleophilic substitution reaction. Reaction in alcohol. Okay, now we are going to see the reactions of alcohol. See, in alcohol, what happens, I have discussed this many times. General molecule is this ROH. Now this OH minus is a poor leaving group in comparison to X minus halide ion. Now this is a poor leaving group, so it cannot go out on its own, right? You have to convert this into a good leaving group first. That's why what happens, we always try to protonate this first, H plus. Say. So this gets protonates and it forms this. And we know this H2O is a better nucleophile, sorry, better leaving group. After this, this goes out and it forms R plus H2. So like this, the SN1 reaction takes place in alcohol. Understood? Any doubt in this? I am not getting any response from any of you.
So not.
Okay. Now, the first reaction of this, you write down alcohol, and the first reaction is very important. We call it as Lucas test. Have you heard about it? Lucas test. For Lucas test, we use a reagent which we call it as Lucas reagent. So that is ZnCl2 with concentrated HCl. This is Lucas reagent. And this test is used to differentiate differentiate 1 degree, 2 degree and 3 degree alcohol. One degree, 2 degree and 3 degree alcohol. So what happens overall, whenever you have an alcohol and this alcohol is allowed to react with Lucas reagent. Lucas reagent is an acid concentrated with ZnCl2. Whenever this is allowed to react with Lucas reagent, it forms alkyl halide RCl and a white turbidity appears here. Okay. The rate of appearance of this white turbidity, with this rate only we determine whether the given molecule is 1 degree, 2 degree or 3 degree. Means the rate at which this white turbidity appears, that signifies the given alcohol is either primary, secondary or tertiary. How you try to understand this? So first of all, what happens, whatever alcohol we have ROH, this with H plus, because we have concentrated HCl here, acid H plus. So this will protonates the hydroxy group and it converts into ROH2 plus, which further converts into R plus plus H2O, R plus plus H2O, and this R plus further reacts with Cl minus ion, forms RCl. forms RCl. Okay, and how this H plus forms here, that also you can understand. Since we have ZnCl2, ZnCl2 behaves as Lewis acid here. HCl takes this ZnCl2, ZnCl2 takes this HCl here, it forms H plus plus. Okay, we'll get H plus here and ZnCl3 minus. Wait a second. Negative. This H plus comes over here, react with this, forms carbocation, and then this. Now the rate at which the carbocation forms, because this step is only the SN1, RDS of the reaction is this. If this is stable, right, carbocation is stable, rate will be more and faster the turbidity appears. Okay, more stable carbocation, more will be the rate of the reaction, and hence we get the turbidity with a faster rate. Okay, so actually what happens if you have 1 degree alcohol, 2 degree and 3 degree alcohol. So 1 degree alcohol mainly follows SN2, 3 degree follows SN1, right? And here the time required to appear this turbidity is in hours. Here it is in minutes. And here it is in seconds. Okay? Because we know 3 degree carbocation is more stable, hence rate will be more in case of 3 degree carbocation, and that's why it forms turbidity with the fastest rate. Okay, so if the turbidity appears in second, it means it is tertiary alcohol. If it take minutes, then it is primary. Sorry, minutes, then it is secondary, and if it take hours, then it is primary. Okay.
So the role of ZnCl2 is a Lewis acid, sir.
Yeah, it takes Cl minus from HCl.
Sir,
Like,
can we use AlCl3 or something else like that?
AlCl3 we can also use for this purpose, but ZnCl2 we are using here. We can have any reason possible. Maybe it it available easier with a cheaper rate. There are many possibilities, right? Or we can also say that it involves a faster rate into this in comparison to AlCl3, right? So that's why we are using ZnCl2. But yes, AlCl3 also has similar kind of function. Okay, but for Lucas test, it is a name reaction. Test is given, name is given of the test, that is Lucas test, and we only use ZnCl2 for this purpose. Okay, it is also possible with AlCl3. Okay, maybe it requires little more time than this. Okay, but if you provide the condition with AlCl3, also similar kind of reaction possible.
So,
whenever we talk about Lucas test, you have to take HCl with ZnCl2. Done. Next reaction you see, Darjan's process. What is this reaction? I have done this reaction in alkane also. Could you tell me?
SOCl2 reaction.
Yes. SOCl2 with
Alkyl, no, an alkane? Not sure.
Alkyl halide.
it is a
No,
reaction of what?
Formless.
so it's to form an alkyl halide. So,
Yeah, it's
Oh
formed
yeah.
alkyl halide, but it is
Alcohol plus
we are
association.
doing reaction of alcohols, na?
oh yeah.
So obviously it is alcohol with SOCl2. Okay. So again in alcohol, I won't discuss this. Okay. So all of you, those who are attending this session, whatever mechanism I'm discussing the mechanism now, but in the class when we discuss alcohol chapter, I won't go into that depth. Okay. The way I'm explaining it now. You see this reaction, the reaction is ROH with SOCl2, right? It forms RCl, sulfur dioxide evolves, and HCl also evolves into this in gaseous form. Byproduct is this, gaseous forms, it escapes into the atmosphere. Okay. Now you know the mechanism of this reaction. What type of mechanism is this?
Is it SN1?
It is SNi, nucleophilic substitution intramolecular reaction. And in this, the configuration does not change. It retains the configuration. Configuration does not change. You must remember this. Okay. Mechanism you see, ROH SOCl2, the molecule is this. It is similar kind of a structure, like we have DMSO, dimethyl sulfoxide. So what happens here, you see, this lone pair attacks onto this sulfur, right? And this pi electron goes onto this oxygen. So we get ROH, and this O attached with sulfur, and sulfur has 2 chlorine atom here with O minus on it. Now in the next step, if this comes out, like if this forms a pi bond here, now if this forms a pi bond here, one chlorine goes out as a leaving group, okay? And this chlorine, which comes out as Cl minus, this then attack onto this alkyl group, right? And when this donates the electron pair here, this will have one positive charge. It takes the bond pair of electron and goes out. So this chlorine takes this R. So it gives you RCl with OH, S double bond O, Cl, right? This further decompose. This bond pair comes over here, H plus takes this Cl minus. This further decompose into SO2 and HCl. This is not important, okay? The important thing is here. Configuration does not change into this. Okay, so this is very important, this one. Configuration does not change. It's very important in this. Have you finished this? You see how it is SNi. SNi is this nucleophile comes over here, this electron pair comes over here, and this Cl minus goes out. This attacks onto this comes over here. So this step is SNi reaction. Now there is one more important reaction in this. Suppose we have a molecule, say a chiral one I'm talking about, OH, and here we have CH3, D and H. Now this is allowed to react with SOCl2 in presence of pyridine. Then the product we get here is ClH CH3D. Okay. In this case, what happens in this reaction here, inversion takes place. Inversion takes place. Okay. So without pyridine, there were no inversion. When you have pyridine, then inversion takes place. Okay.
How, sir?
I'll explain this. Why you see this, when you have an alcohol, ROH, lone pair, plus SOCl2. SOCl2. Then what happens? Same step, this comes over here and this goes on to this oxygen. So it forms ROSCl, Cl, single bond O, negative charge. H here will have the positive charge. Okay. Now after this, there's a change. And what is that change? Since we are using pyridine here, so this pyridine act as a base, weak base actually, and to stabilize the positive charge on oxygen, this takes this H plus from this, right? And then it converts into ROSCl, ClO negative. Okay. Now, when this oxygen forms the bond pair, this Cl minus goes out. So we'll get ROS double bond OCl. And in the next step, this Cl minus which comes out here, this behaves as a nucleophile attack onto this carbon atom. And this bond pair is taken up by this sulfur. Okay. So this converts into RCl, right? RCl. This bond pair comes over here and leaving groups goes out. SO2, Cl minus. This Cl minus will take this H plus here, forms HCl and pyridine. So this attack here is the SN2 attack. And that is why the configuration of this changes over here. So that pyridine takes this H plus, this comes over here, Cl minus goes out. Now the attack of Cl minus on this alkyl group is what? Is SN2 attack. That's why the configuration changes. See, all these mechanism has been explained on the study which is done on these reactions. Okay, so you have to keep these things in mind that in presence of pyridine, there is inversion in configuration. Without pyridine, there is no inversion. Okay, once you keep these two lines in mind, then you'll understand what could be the possible mechanism. Obviously, it requires some practice, but the conclusion you must keep in mind. Done?
Yes, sir.
Okay. Next reaction you see. The reaction with PCl5. 3 molecules of alcohol with PCl5. The mechanism is SN2 and it forms RCl plus POCl plus POCl3 will get. Just a second. RCl with POCl3 and HCl, correct. Mechanism is SNi also involves into this, SNi and SN2. Both method we have here, along with SN2. Okay. So first of all, you should know how to write down the product into this. I will suggest you to write down the product into this directly. The mechanism we can discuss, but the mechanism is not that important here. Okay. You should know how to write down the product with PCl5 or PCl3. So how to write down, you see the alcohol we are having ROH, right? And PCl5, the structure you see, the PCl5 has trigonal bipyramidal structure like this. Cl, Cl, Cl. This is trigonal bipyramidal structure. We have 2 axial bond, and you know axial bond are longer and weaker. Okay, 2 types of bond we have, axial and equatorial. These 3 bond in this plane of triangle, it is equatorial. These 2 are axial bond, it is a weaker bond. Okay, and that is why this PCl5 easily dissociates into PCl3 and Cl2, right? And this conversion increases, the reaction goes in forward direction as temperature increases. More temperature, more amount of PCl3 you'll get. Okay, that you also keep in mind. Not that important, but just an information. As temperature increases, amount of PCl3 forms also increases. Correct? Now, how to write down the product with this alcohol? So what I'll suggest, I'll just write down the, the molecule structure like this, with the 3 chlorine atom written like this. Okay. Now, 1 chlorine goes with hydrogen, another chlorine goes with alkyl group, and rest is attached with this phosphorus and oxygen. So we get here RCl plus HCl plus POCl3. This is the product. RCl plus HCl plus POCO3. Reaction involves both SN1 and SN2 mechanism. Okay, so this you must remember. This is important, how to write down the product. Okay, here. So I'll suggest with PCl5 and PCl3, you must know how to write down the product. I'll show you the reaction of PCl3 also. Write down reaction with phosphorus trichloride. And in pentachloride PCl5, we always get POCl3 as one of the product. Okay, here we are taking 3 molecules of, just a second, let me just check this. No, we are not taking 3 molecules here. Only 1 molecule we are taking. That's why I say only 1 molecule we are using. 3 molecules we take in PCl3. So 3 molecules of ROH plus we have PCl3. The mechanism here is SN2 and we get 3 molecules of RCl plus we'll get H3PO3. This is the reaction we have. Okay, since it is SN2, so configuration will get reversed. Okay, now you see this mechanism here. If you have ROH plus PCl3, the vacant orbital here we have on phosphorus. This lone pair comes over here and it forms ROPCl3 oh, just a second. When this attacks over here, this goes out as leaving group. So one Cl won't be there. So it will be like this, H positive charge and Cl. So finally this converts into H plus comes out. This converts into RO, PCl and Cl. Okay? One lone pair will have on this, one lone pair will have on this, one lone pair will have. Now since we are using 3 molecules of this, so the other 2 ROH also reacts with this molecule in the same way, and it finally converts into, with 2 molecules of ROH, it finally converts into this. With one lone pair present here. 3 Cl minus goes out. Now this 3 Cl minus attacks onto this R and this O minus goes out. So when you have 3 Cl minus, so one by one it will attack onto each of this alkyl group, forms 3 RCl, and PO3 minus will take 3H, forms H3PO3. This is the product we get. So this attack of chlorine here is SN2 attack. Retention, inversion of configuration. Understood?
Sir, the alcohol can be 1 degree, 2 degree, or 3 degree, anything.
SN2 we have, so alcohol must be 1 degree we'll take here.
Okay, sir. Sir, and with PCl5?
PCl5 is, so you can find out the hybridization, no? You're
No,
talking.
sir, not hybrid. Sir, in reaction with PCl5, can it be 1 degree, 2 degree,
Same
3
thing,
degree?
same thing. SNi and SN2 we have. R is not a factor here, right?
Okay.
Obviously, SN2 hai to 1 degree, 1 hai to 3 degree.
Okay. Sir, so in that also it can't be 3 degree.
One thing, I'll tell you one thing. 1 degree, 2 degree, better you don't keep in mind. It is there, so it's fine. You just keep one thing in mind. If there is any possibility of getting stable carbocation, just say for example, if it is possibility of getting benzyl carbocation,
Yes, sir.
benzyl carbocation, then also it is SN1. Allyl carbocation, then also it is SN1, right? So 1 degree, 3
Yes.
degree is fine, but main objective is what? That if the possibility of forming a stable carbocation is there, then the mechanism will be SN1, provided that other conditions are there. like nucleophilic condition, like property of nucleophile must be weaker nucleophile, and solvent. Okay, but here you don't have to think about this. Let's say what I said, Williamson ether synthesis, it is SN2 mechanism, correct? So you don't have to talk about what is the degree of alkyl halide there. You have to keep this in mind that Williamson ether synthesis is SN2 only.
Yes, sir.
Okay, alkyl halide must be 1 degree there. It is SN2, right? Similarly, here also the reaction of PCl3 with ROH is SN2. Right? PCl3 with alcohol is SN2. Because you see, you are only talking about the degree of alcohol, correct? 1 degree, 2 degree, 3 degree, you are saying.
Yes,
We
sir.
have other factors also. We have the factor of nucleophile, right? We have what solvent we are using, right? We have what, the other things also we have into this. So all factors you cannot apply in any reaction. Means if you are going to think about the factors which affects all those SN1 and SN2, you will get confused. So what I am suggesting you, like I said, Williamson ether is SN2. You have to keep that in mind. It is SN2. Don't consider the factor of substrate, 1 degree or 3 degree. If I told you this PCl3 is SN2, you have to keep this in mind. It is SN2. Because for this reaction, we must have certain solvent, right? We must have certain condition of this reaction. So whatever whatever the required condition we have for this reaction, overall it favors SN2. That is what we can understand. When you talk about the degree of alcohol, you are considering only one of the factors.
Yes, sir.
Right? So the overall effect of all the factors leads to SN2 mechanism here. Right?
Okay. Understood.
Yes. Especially this PCl5 and PCl3, you just keep this in mind that if you have PCl3, H3PO3 always goes out. ये common है reaction सारे में. Right? If you have PCl5, then obviously POCl3 goes out. That is also common in all reactions. Okay? So common thing you should keep in mind. जैसे देखो मैं एक PCl5 का I can give you one more reaction. Suppose we have ether. Ether का reaction, write down in this. Reaction of ether with PCl5. Reaction of ether with PCl5. Now, since I told you that in PCl5, POCl3 goes out, right? This gives you an idea that what could be the possible product here. For example, you see मैंने ether लिया ROR2, correct? इसका reaction with PCl5, ठीक है? कैसे लिखोगे product? मैंने trick बताया तुम्हें. What you will write? Phosphorus, you write here. Chlorine, you write here. Chlorine, you write here. And the 3 chlorine, you write this way. Then you break this bond, so it forms R1Cl plus R2Cl plus POCl3. This is the product of this reaction. Is it clear?
Yes, sir.
Even if you have this kind of compound, you see, epoxy compound, if it is there, then also you can write down the product in the similar way. Like I said, epoxy ऐसा कुछ compound है PCl5 के साथ. Try writing down the product in this way. What I'll do, you see, मैंने लिखा phosphorus, chlorine this side, and the 3 chlorine will have here. So this carbon will go with this chlorine. I'll just change the color. This carbon will go with this chlorine. So what we'll get? We have a ring and one Cl here, one Cl here with POCl3. You see, in all these reactions, POCl3 will go out if you have PCl5. So ether reaction is this. Cyclic ether, we have similar kind of reaction. Even you can write down the product of reaction of PCl5 with acid, amide, aldehyde, ketone in the similar way. What I said, ether dekh liya, cyclic ether you have already seen, same kind of compound. Alcohol reaction you have seen, same kind of product we are getting. Okay, this thing is true when you write down the reaction with acid, amide, ketone and aldehyde. I'll show you. Just you write down the reaction of PCl5. Further, some more reactions of PCl5 I'll show you here only. However, this was not our topic that we were discussing, but let it finish it here only. Suppose we have an acid, right? Carboxylic acid. This reduces your effort. Okay, if you find out the pattern, how the reaction is going on, you can keep this in mind. Okay, all the product that you are getting. Acid है तो मैंने क्या लिखा? मैंने लिखा RC double bond O OH reaction with PCl5. So what happens? You see again the same thing. Phosphorus oxygen के पास I wrote phosphorus Cl Cl and 3 chlorine atom here. Now you understood what is the possible product. This goes this way and this goes this way. So you'll get what? Acyl chloride plus HCl. Again you see you're getting POCl3. Any doubt? Tell me, any doubt guys? Amide. Could you write down the product into this? RC double bond O NH2. With POCl, with PCl5. This is a different reaction. Only this we have the exception here. I'll write down the product here, just you wait. First you write down the answer in this reaction. C double bond O and H we have here. PCl5. Here also I'll suggest all these are Cl. So what happens? One of the bond here will take this chlorine, another one will take this chlorine, and this phosphorus will go with this oxygen. So you'll get RCH, and we have 2 chlorine here. This is the product we get, plus POCl3. In this reaction, it is dehydration reaction leads to the formation of cyanide here. This we'll discuss in nitrogen containing compound chapter, but I have written this, all the reactions of PCl5, so I've given you this. Only here we have the change. How do you memorize this? You just take these two hydrogens, this two hydrogen with this oxygen. And we have a double bond here, we'll get this. So dehydration reaction takes place with amide. Another reaction, the last one here, the reaction of ketone of PCl5. Suppose we have a cyclic compound with PCl5. Same thing you have to do. Product would be what? Is it clear? You understood this? So in all these reactions, like I said, PCl3, PCl5, okay, Williamson ether synthesis reaction. In all these reactions, you don't have to get concerned with uh, the degree of alcohol or alkyl halide. Okay, it is fixed. It goes like this only, always. Did you understand this? So PCl5 reaction is important. Okay, you must understand the pattern here that we have discussed just now. Okay, now we see the other reaction. In this reaction, you have to consider the degree of alcohol. In this kind of reaction you can consider. I'll show you what reaction it is. See, write down the reactions. We are talking about the reaction of alcohol. So reaction of alcohol with HX. With HX. So generally what happens, I'll tell you this, generally what happens, that if the alcohol is 3 degree, 2 degree, 2 degree means the solvent is polar protic and weak nucleophile, or the alcohol which are getting stabilized through resonance stabilized, write down it properly. It's not resonating structure, it's resonance stabilized. So if this is the condition of alcohol we have, then the reaction mechanism is SN1. Okay. But if it is 1 degree alcohol, then it is SN2 that we know already. Okay. So general reaction is what? ROH reacts with HX. It gives RX alkyl halide plus H2O. Okay. Rate of this reaction is 3 degree alcohol, then 2 degree, and then 1 degree. If you compare the rate of HX, this is for alcohol. If you compare the rate of HX, that would be maximum for HI. Then we have HBr. Then we have HCl. Okay. For HI, the reaction of HI with alcohol, we generally do not require any catalyst. No catalyst required, because it is highly reactive. You see the reactivity order is this. Okay. Rate of the reaction or reactivity order is this, right? HI reacts with higher rate means its reactivity is very high. So HI reactivity is sufficient enough. It does not require any catalyst. But for HBr, the reaction takes place in presence of an acidic medium. We can take H2SO4 for this purpose. For HCl also, we take ZnCl2. These catalysts are required for the reaction of HBr with alcohol. Why? Because this reactivity is less. To promote the reaction, we use some catalyst here. Understood, guys?
Yes, sir.
Yes.
See, I know all these are very difficult to grasp here because there are many things going on. Okay? So it's completely fine that you are getting only 40 or 50% of it. It's completely fine. Don't worry with it. But you have to revise this twice at least on your own. Then you'll start getting this. Then these things will get into your mind. Okay? So if you are doing it once, you will get confusion, and it is difficult to grasp all these things in the single attempt. Okay, so twice or thrice you have to do this, then only the things will get into your mind. Okay, so like I said, reactivity order HI is most reactive, does not require any catalyst, HBr and HI. So now you see this reaction, ROH ka reaction with HI. Could you tell me the product here? Could you tell me the product here, guys, first?
Are they?
Yes. Still waiting.
Sir, Ri plus H2.
Ri plus H2. Why don't you reply first? Ri plus H2O. Does this reaction requires any catalyst here?
No.
No. Why doesn't it require any catalyst?
Highly reactive.
Because HI is highly reactive. So they can frame this kind of question. In your board exam also, they can ask you this kind of question. Why we need catalyst for addition of HBr? Why not for HI? Okay. Reactivity is the reason. Okay. So this is mono alcohol, right? For diols also, we can have this kind of reaction. Diols means CH2OH, CH2OH. Could you tell me how many equivalents of HI required for this?
2, sir.
What?
Is it 2, sir?
2.
2, because 2 OH we have, so 2 equivalents required. So it converts into CH2I, CH2I, and 2 moles of H2O goes out. Okay. But this product is also not that stable. It has tendency to convert into an alkene with elimination of iodine, I2. Okay. And further, if you are using excessive, if you're using 2 moles of HI, you'll end up getting this. Okay. It is again a bit different kinds of compound you are getting. Okay. So again, this is different. So must keep this in mind. This compound is unstable. If iodine atom is present at adjacent carbon atom, it is a bit unstable, right? And that is why these two I2 molecules goes out and forms an alkene. So if you are getting 2 molecules of HI, you'll get this. Okay. Further, if you insert or add HI into this, then this will be the addition reaction of HX on alkene. And according to Markovnikov or anti-Markovnikov rule, depending upon the condition, it converts into alkyl iodide. Did you understand this? This diiodo compound that you have here, it is unstable. It is vicinal diiodide. Like we have vicinal and diol, it is also vicinal halide. Okay, dihalide. Unstable, converts into this, and then if you add HI, you get into alkyl halide. Okay? Or if I write down in one single step, मैंने यहाँ पे 2 HI लिया है. If I take here excess of Hi, if I take here excess of Hi, then what happens, will end up getting this molecule directly. You won't get vicinal halide, means the path of the reaction is this. Obviously this molecule converts into this via this route, right? But eventually you'll get this. If you're using only 2 Hi, you'll get an alkene as the product. Further, if you add Hi, you convert into this. Or here only, if you take excess of Hi, you end up getting alkyl halide. Understood?
Yes, sir.
Yes, sir.
Now, based on this only, we'll see the last reaction. Based on this only, if you see, we have this reaction of triol. Okay, triol, the reaction is CH2OH. CH2OH. This is important. JEE may they have asked this question once. Okay, triol.
Sir, CHOH, sir.
Yes, CHOH, my bad. CHOH, okay? You'll get this. Now, if you're using HI excess, correct? So what you will get, tell me? Excess hai, to sabse pehle, all the hydroxy group will get replaced by the iodine. And we know 2 iodine atom at adjacent carbon is not stable at all. So I2 goes out and we get a double bond. It is the same reaction actually. Plus I2, no doubt. But we have excess of Hi. So this Hi again react onto this ring, onto this double bond alkene. So this converts into CS3, CHI, CH2I. Now you see where this product is going on. Again 2 iodine at adjacent carbon, it is not stable at all. It converts into alkene again. You'll get CS3, CH double bond CH2, and I2 goes out. But since we have excess of Hi, so in the last, again we have addition of Hi according to Markovnikov rule. This gives CS3CH, CS3I, and this is the final product in this reaction. How many of you understood this? You can type CLR quickly. Quickly guys, just the last thing we have done. We'll wind up the session now. Correct. So what happens here, you see, you only have to keep one thing in mind for this kind of reaction. First of all, it is the reaction, substitution reaction. So I minus replaces this OH, you'll get this. 2 halogen atom at adjacent carbon is not at all stable. So what happens here, it eliminates I2 molecule and forms a double bond, which continues to this, and you'll end up getting alkyl iodide according to Markovnikov rule. So when you haven't done this reaction before, in the exam, you can't even think that we have 3 OH with excess of Hi, you'll end up getting this product. You can't even think about it. You'll get something like this or some other thing, it will be there. Okay. So all these things are very important even before the exam, or you have to revise this on a regular basis so that you can keep these things into your head. Okay. So it's very important. Diol wala reaction they have asked once in JEE. This one they have asked once in JEE. Okay. Triol, I don't see, they haven't asked probably, but maybe may not be, they can ask. Okay. You cannot eliminate any probability here. Right. So these are the reactions, few reactions of alcohol we have discussed. There are many other reactions of alcohols, ether. We'll finish that next class and then we'll start elimination reaction. Okay. So we are done with 99% of reactions of nucleophilic substitution. Okay. Just now, I'll share one assignment with you on reaction mechanism. You can solve those questions. There are many things into that, but till elimination, you can solve those, you can attempt those assignments. Okay. So I'm going to share the assignments on the group now. You can give it a try. Okay. Anything else, guys?
No, sir.
No, sir.
Chalo, we'll wind up the session here. Okay. For extra session, we'll keep you updated. Okay. We'll tell you.
Yes, sir.
Thank you, sir.
Okay. Thank you. Bye-bye.
Thank you, sir.
Thank you, sir. Thank you.
Yes, sir.
Thank you, sir.
Thank you, sir.